Welcome to This Explainer. You know, for years, the inner workings of massive language models like Claude have pretty much been treated as the complete black box. But recently, researchers over at Anthropic achieved what is honestly a fascinating breakthrough. They've actually discovered a way to uncover an AI's hidden, silent reasoning. Literally, the thoughts it holds right before it speaks. So today, we're going to look under the hood at the exact mathematics that makes this incredible feat possible.
I mean, it sounds straight out of science fiction, doesn't it? Can math actually read an AI's mind? Well, as we'll see today, by using some seriously clever calculus and linear algebra as a sort of magnifying glass, we can essentially read the internal ticker tape of concepts an AI is weighing before it ever outputs a single word.
Okay, let's dive right in. Here is our roadmap for the explainer. First, we'll go inside the AI black box. Then, we'll measure causal sensitivity. Third, we'll look at filtering noise through averaging. Fourth, we'll translate that math into words. And finally, we'll reveal the JSpace. Simple enough, right? Let's get to it.
Starting with Section 1. Inside the AI black box and the limits of the old lenses we used to rely on. Think about this classic multi-hop logic puzzle for a second. The prompt is, the number of legs on the animal that spins webs is. Now, to get to the correct output, which is 8, Claude needs to use a silent intermediate concept. It has to realize, without saying it, that we are talking about a spider. But the word spider is never actually spoken by the AI. It's a completely unspoken working variable. The huge question for AI researchers has always been, how in the world do we see that silent concept when it's just buried deep in millions of mathematical activation dimensions?
Well, in the past, researchers used something called a logit lens. This older method kind of naively takes an intermediate layers vector and decodes it directly using the final layers vocabulary dictionary. But that completely fails in the earlier layers because the coordinate space actually changes as data moves through the model. It's kind of like trying to read a French document using a Spanish dictionary. It just doesn't work. But Anthropic's new Jacobian lens, or J-lens, completely flips the script. Instead of that naive decoding, it mathematically calculates how an early concept physically ripples forward to influence a future output.
Which brings us to Section 2, measuring causal sensitivity, the true mathematical engine running all of this.
Now, what's really interesting about this is the core mechanism, the Jacobian matrix. If you remember your calculus class, a derivative just measures a rate of change, right? Well, the Jacobian matrix is a massive grid of partial derivatives that acts like a sort of butterfly effect calculator. It measures causal sensitivity. It's essentially asking, if I make a tiny, microscopic nudge to a mathematical vector in, say, layer 10, how does that mathematically ripple forward through all the subsequent layers to alter the final output token?
And here is the exact step-by-step pipeline for how they do it. First, the math applies a tiny nudge to an intermediate activation vector, which we'll call HL. Second, it propagates that shift all the way to the final layer's output, called Hfinal. And third, it calculates the first-order linear effect. This is absolutely revolutionary because it's tracking actual causal clues. It isn't just correlating data. It's practically proving that an inner layer concept has a direct physical consequence on the model's final decision. Moving right along to Section 3, filtering noise through averaging, or how we actually find the signal in all this math. Now here's the catch. If you calculate a Jacobian for just one single prompt, you get a really messy picture. A single prompt conflates the model's true general understanding of a concept with the noisy specific context of that one sentence. To fix this, Anthropic researchers average these Jacobians over 1,000 diverse prompts and multiple token positions. This massive averaging acts as a super-powered noise filter. It strips away all those context-specific artifacts and isolates the model's stable general disposition to say a specific word. Basically, it finds concepts that are truly verbalizable across any situation.
And that brings us to Section 4, translating math to words, the final decoding process. Just look at this incredibly elegant formula. We take a dense, entirely unreadable vector from deep inside the model, multiply it by our Jacobian matrix, and then push it through an unembedding function. This single, concise line of code is literally what transports an alien mathematical concept out of the AI's depths and prepares it to actually be read by us humans.
And this brilliantly illustrates the final step, the unembedding matrix, or WU. Every language model has this built-in translator sitting at the very end of its architecture.
It's the dictionary that takes continuous, flowing vector math and locks it into discrete, human-readable vocabulary words. By multiplying our average Jacobian vector with this unembedding matrix, we get a ranked list of the exact words the AI is holding in its mind at that exact intermediate layer. Finally, Section 5, revealing the JSpace and the macro implications of this entire process.
You might naturally assume that this hidden reasoning space takes up the entire brain of the AI, but researchers found it's actually incredibly sparse. The JSpace, this privileged area containing reportable, conscious-like thoughts, occupies at most 10 to 15% of the total activation variance. It's a highly specialized, remarkably narrow channel right in the middle layers of the model, dedicated strictly to flexible, reportable reasoning.
So, what is the crucial takeaway here? Well, it is absolutely critical for AI safety. Because the JSpace acts as a direct window into what the model is thinking but not saying, we don't have to just blindly trust the AI's final text output anymore. In red team auditing, the JLANs actually caught words like manipulation, trick, and blackmail lighting up in the JSpace long before Claude ever acted on a hidden goal or fabricated data. It's silently detected prompt injections. We can literally catch deception in the math before the AI even speaks a word. It's a real game changer.
Which leaves us with this final thought. If a simple, calculated average of partial derivatives can reliably reveal an AI's hidden, unspoken thoughts, how close are we to truly understanding machine cognition? We now have a mathematical flashlight to shine directly into their darkest cognitive corners. Thanks so much for joining me on this explainer. Keep questioning the architecture around you.